everyone. So today we are going to go through independent events and dependent events. So I'll explain what they mean in a second. But what we're doing overall today is we're going to do some problems, these three. Hopefully you'll find them interesting. I definitely do. And we're going to talk about gambling at the end with an example problem. So let's get into it. Okay, so firstly, let's try and I want to ask you this question and ask whether you find it difficult or easy. So here we go. I flip a coin twice and get 2 heads. Okay, so what is the probability that I get a head next time I flip the coin? Now, a lot of people think when they see this question, here's what they think. They say, well, we've got 2 heads already. And so it's unlikely that I'm going to get a head again, because then I would get 3 heads in a row, and that seems very unlikely. Now, that's not the right thinking, because flipping a coin the first 2 times and flipping a coin the next time are independent events. What that means is they don't influence each other. If you flip the coin twice and you get 2 heads, that does not change the probability for the next time you flip the coin. If you think about it, you're still holding a physical coin in your hand and you're still flipping it, and whether it lands on heads or tails is still a 50-50 chance. Doesn't matter that you've got 2 heads beforehand. The probability is 1/2 that you get a head next time, just like it is every other time. Okay, so this question is actually very easy, but you have to recognize that it's independent. Getting ahead, the first two heads, that's independent of whether you get a head or a tail the next time you flip it. It's still 50-50 chance. Okay, let's keep going. Hopefully you'll find the next question easier now. Well, let's see. A couple has 2 daughters. What is the probability that they have another daughter? So if you think about it, nothing has changed. It's still just as likely that you get a daughter as they have a daughter as they have a son. So these are also independent events, and the probability is still roughly 1/2 that they have a daughter instead of a son. Okay, so let's go for the third one. A bag contains 2 rocks and a diamond. I put gardening gloves on so I can't tell which one it is by feeling it, and I remove one of the rocks. What is the probability that I choose a diamond? Now, initially at the start, you have 2 rocks and a diamond, so if I was just to choose, if I didn't remove one of the rocks, let's say this didn't happen, then the probability would be 1 successful outcome out of 3. But the fact is that after I've removed one of the rocks, I only have 1 rock left and 1 diamond. So my sample space now, after I move the rock, is 1 rock and 1 diamond. So now the probability has now changed. The probability now is 1/2 because 1 out of the 2 is a diamond. So removing a rock at the start and removing something else, they are dependent events, because it actually matters. If I have 2 rocks and a diamond, it actually matters what I get the first time around. If I pick one, that will change what I get in the second time round. And we're going to get into this in a little bit later. But these are dependent events because one thing depends on the other. Your choice in the probability of your choice in the second time you choose something depends on what you chose in the first time round. All right. So now let me show you, let's draw a tree diagram for this particular situation. A bag contains 2 rocks and a diamond. I take out one item, put it back, and then take another out. So what is the probability that I choose the diamond at least once? So we're going to draw a tree diagram, and I want you to think about whether the 2 items that you choose, whether they are dependent or independent. So in our tree diagram, we've got stage 1, where you take out the first item. So there's 2 rocks and 1 diamond. And then we've got stage 2. So in stage 2, let's see. Okay, let's say I pick out a rock the first time, but I have to put that rock back and then I have to take another item out. So I could take this rock twice in a row, or I could take this rock and then take the other rock, or I could take the diamond. So each time, you've still got the same 3 options, rock or diamond, because you're putting the first one back. So we've got rock, diamond. Okay, so it says, what is the probability that I choose the diamond at least once? So let's write out the sample space over here. We got 2 rocks, a rock, and then a diamond. Rock, diamond, rock, diamond, rock, diamond, rock, diamond. Okay. So which ones are successful? The ones with a D in there. So that would be this one, this one, this one, this one, this one, this one. So that means the probability there's 6 of them, that would be 6 successful outcomes over 9 in total. Now, keep in mind, we could do this formula because the probabilities are all the same. Each one of these outcomes, the chance is the same. Okay, so now we're going to go through a different question, and you'll notice that in the middle there's no replacement of the item. So you don't put the item back in this question. The item just, if you take it out, it stays out. So I'm going to show you a way of doing this, and this is not the most efficient way of doing it, but it's a way of doing it. So let's do it. Let's say you write all of the possibilities down. So you write down the rock, and the diamond, and these are all just as likely as each other. So the probability of each of these is 1/3 because there's 3 of them, and they're just as likely. Now, because I'm not replacing them, I only have 2 options after I take this rock out. The 2 options are the other rock and the diamond. The probability of getting the rock is 1/2, and the probability of getting a diamond is also 1/2, if I know that I've already taken this rock out. If I take the other rock, I could get the first rock or I could get the diamond. And the probability for each of these is 1/2 as well. And finally, if I take the diamond out, I just have 2 rocks. And it's just as likely that I get either one of those. So that's 1/2 for each of them as well. Now, if I want to find out the probability of any of these outcomes, which I'm just going to write down, what I could do is I can multiply the fractions on each branch leading up to the path, or each branch of the path leading up to the outcome. So I said in a previous video that I'd go through this, and so here we are, and I'll go through it. So the key for this, and let's look at getting this rock and this diamond. And I'm going to write the 1/2 first. because a half times a third is the same as a half of a third. Now, you take the rock. That's the first thing that happens. So the probability of that happening was a third. And now this is half of that third. And so the overall probability of getting this path is a half of a third, which is a half times a third. That's why you just times them together. And what that means is each of these is actually a half times a third. So all of these, the probability is 1/6. So now, if we're answering the question, which we are, what is the probability that I choose a diamond? Probably the quickest way to do this for this question is because they're equally likely, because they're just as likely as each other, I just count the outcomes that are successful, which is 4 in this case, and so the probability is 4/6. In the next question, we'll do our setup will involve outcomes that are not just as likely, and so we can't do this, but because they're all 1/6, we can just do this simple operation here. All right, now I'm going to start doing this question the same way as we did the other one. The only difference is this one had 2 rocks and a diamond, and in this one, there's 19 rocks. So let's start off and we'll do the same thing. So I have to draw 19 lines. And obviously, you're thinking of quitting the video now because this is not going to be a fun video if I'm just drawing 19 lines and then I have to draw 19 more lines for each. No, and I'm not going to do that either. So is there a simpler way of doing that? Yes, there is, because there's no real difference between any of the rocks, is there? For the purposes of this question, there's either a rock or a diamond, but it's just the case that there's a lot more rocks than diamonds. So what I can do is I'll set up a tree diagram where the outcomes are not equally likely this time. The probability of getting a rock the first time is 19 out of 20, because 19 successful items, or 19 rocks, and 20 items in total. And the probability of getting a diamond is 1/20. So then, there's only 2 options, except if you choose a diamond the first time, there's only one option, isn't there? That's choosing a rock. But if you choose a rock, that diamond is still there, so you could still get a diamond. Now this is where it gets a little bit more interesting. If I choose a rock the first time, then the second time round, how many rocks do I have in there? Well, I have 1 less rock, so that's actually 18 rocks. And how many items do I have? I have 19 items because I've taken one of them out. So this rock actually affects both of these numbers. Now, if I take the rock out, how many diamonds do I have left? Because we're trying to find the probability of getting this diamond, we have to think about how many diamonds are in there. Now, there's still 1 diamond. But how many items are there in total? There's 19. Okay, and now getting the rock here, because there's only one option, the probability is 1. Or another way to think about it is 19/19. Because there's 19 rocks and there's 19 items. So there we go. Now, what is the probability that I choose a diamond? In this case, we still look for the successful outcomes. So here's all our outcomes. There's only 3 things that can happen. And 2 of them are successful. This one and this one. Now, we have to think about what's the probability that I choose a diamond. Now, I've just said in this one that you can actually multiply the probabilities on the branches. So let's do that. And we have to add up these 2, actually. So we'll find this one, which is RD, the probability of RD is 19 over 20 times 1 over 19. And this is pretty lucky, actually, because we can cancel out these 19s. But we're not finished yet. I'm just going to say probability, oops. So we know what we're doing. Probability of getting a diamond is this plus this one, which is 1 over 20 times 19 over 19. And keep in mind, that's equal to 1, isn't it? So now we're going to cancel out our 19s. So then we'll have 1 over 20. And then we've got plus 1 over 20 times this. This is equal to 1 over 1. So that's 1 over, if I want to times these two fractions, I just times the ones and then times the bottom. So I have 1 times 1 is 1. 20 times 1 is 20. And so I've got 1 over 20 plus 1 over 20. Luckily, the denominators are the same, so that's 2 over 20, which is 1 over 10. So that's fairly complicated. I'd recommend that you watch that again, just this section, if this was a little bit tricky. And you'll soon see that, hopefully it'll soon click into place, the understanding of that. Okay, now we're just going to move on to the final section, which is about gambling. So this is another example of dependent events. So let's say you're thinking about playing a game. Playing the game costs $110. In the game, you draw 2 slips of paper from a bag. On the slips of paper are the letters A, B, C, and D. You win different amounts of money for each letter. So A is worth $10, B is worth 20, C is worth 50, and D is worth 100. Now, what you're aiming to do, obviously, in this game is to have more money at the end than what you started with. Then you'll have won some money. So this is obviously the appeal of all gambling is winning money. So let's see, what's the chances that I'll have more money at the end than what I started with? Now, for this one, you could draw a tree diagram, but that's going to be a lot of effort still, because you have 4 options and then you've only got 3 left each time. If I choose A, I can't get A again, so I could get B, C, or D, and you could do that. So there's an easier way. Because there's only 2 stages, I can just do a table. And let's say this is the first choice. And the second choice is down here. Now, can I get A, draw A, and then A? No, I can't, because I'm not putting the slip of paper back. I can't get B and then B because I'm not putting it back either. Can't get C and then C. Or D and then D. So, really, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes. If you get A and then B, you get $10 plus 20, which is 30. And if you get, sorry, that was B and then A. If you get A and then B, you get 30. So it doesn't matter which order in this particular case. So then we can keep going. C and then A is 50 plus 10 is 60. This is 60 as well. So, which ones of these are successful according to the question? The event that we're looking for, and we have to find out which outcomes are in this event, is having more money at the end than what we started with. So 150, 150, 120, and 120 are the only successful outcomes because 110 is the same amount of money as what you started with. So that's 4 outcomes out of 12, which is 1 over 3. Now, that we've found the answer. Now, I want us to think about this. I want you to think about whether you would play this game. Now, it doesn't seem that likely that you would win anything, but keep in mind that there's also two outcomes where you would not win anything, but you wouldn't lose anything either. So those outcomes are okay. And these outcomes are good, of course. And then we've got 6 outcomes that are bad. So you might think, okay, 6 outcomes are acceptable and 6 outcomes are bad. So you might think, okay, for half of these outcomes, I wouldn't mind the outcome. It would be a good outcome or an okay outcome. And for 6 of them, for the other half, I wouldn't like that outcome. So you might think that this game is an okay game to play. But there's always sneaky ways in which over the long run, if you go to a casino, they will win more money than you in the long run. So let's think about this one. The reason that they will always win more money than you is not only that there's more outcomes that are not successful, and by successful, and this time I'm not just using probability language, I'm saying there's a lot of outcomes where you lose money, but also you lose a lot more money in these outcomes than you win if you're successful. So you only win $40 at most, so 150 minus 110. But the amount you could lose is $80 at most. And if you lose money, the smallest amount of money that you could lose is $40. So I guess I'm trying to build an argument here that gambling is not going to get you any money in the long run. There's a reason why casinos run, and the reason is because they usually win. Anyway, okay, that'll be it for today. Thanks for listening this far, and this may be the last video in the series. We'll see. Okay, see you later.